Hello and welcome to Lecture 2 of the Essential Tools for Data Science DeCal. So in today's lecture, we are going to be talking a bit more about the data analysis process, as Uma mentioned in Lecture 1, and specifically, we're going to be talking about data manipulation and wrangling with patterns, Part 1. So quick logistical reminder, please remember to join our Discord. We have it up and it is a bit more informal than Piazza, so we can do that since you're a decal. And over here, you can meet other people doing the course, as well as talk with the TAs in a more relaxed atmosphere. So my name is Siddhant, and I'll be one of your TAs this semester. And today, I will be instructing this lecture along with my friend Elton. A bit more about me. I'm a freshman currently doing computer science. I'm from Bangalore, India, and I did recently start baking during quarantine. So very terrible. Well, I bake a lot of banana bread. And here's my email and my Discord. So if you ever need something, feel free to reach out. Or if you have any questions about the course or life in general, I'd love to talk. Okay, so the plan for today. So we're going to start off with an introduction to Pandas, which is a data analysis library in Python, which is extremely useful, and you'll be using a lot of it throughout this class. Then we're going to talk about the two main elements of Pandas, which are data frames and cities. And then Elton will take over, and he will talk a bit about core Pandas operations. So we have indexing, filtering, and utility operations. Okay, so we also do have the demo data link, which is essentially a Jupyter notebook that has the same demo that we're using in the lectures, and you can follow along if you click this link. This link is also available in the YouTube description, so feel free to find it over there and follow along with this lecture. Okay, let's get started. So before talking about pandas, I want to talk a little bit about the data science process. I think Uma briefly mentioned this in the first lecture, but I want to delve a little bit more into it. So over here, you can see a pretty neat diagram which details the data science process and breaks it up into 5 main parts. So the parts in order are gathering data from relevant sources, cleaning data to format them to formats that a machine can understand, finding patterns in the data, constructing models, and putting the results in good use. Okay, so the first part is gathering data from relevant sources. And this is quite an important part of data science because, well, without data, we can't really use anything. So relevant sources in this case can include a lot of sources. So in this class, we'll primarily be using pre-prepared datasets from websites such as Kaggle, but in the real world, you have a ton of options for gathering data. So you could use pre-prepared data sources, you could gather it on your own, or you could use tools like web scraping in order to gather it off the internet. Next, we move on to scrubbing the data. So once we have the data, we need to make sure that everything works out. There's no weird entries. We have all the entries, and that's where scrubbing comes in. So just as a side note, Pandas is really, really important for scrubbing. So just keep that in mind. That's the main part we could focus on, and a bit of exploration as well. So essentially, cleans data formats that machines, well, and humans can understand. And after we're done scrubbing the data, after we're done cleaning it a bit, we can move on to exploring the data, which I think is one of the most important parts of the data science process. So over here, we can use tools such as visualization, we can use statistical inferences to explore correlations between variables, or we can explore any interesting patterns that in the data that can lead us to some interesting hypotheses about what's going on underneath the data. And once we've done that, we can build upon this hypothesis to model certain predictions. So let's imagine that I have to make a predictor. I have to make predictions for housing prices in the next year. And let's say I have data for the last 5 years of housing prices in a certain area. So I already have data. So I've collected data from, let's say, a pre-prepared file, or I've scraped the web and gotten it. And then I can scrub the data to make sure that the variables are in order. I don't have tons of missing data, things like that. And then after that, I can use statistical processes. I can use visualizations. I can use graphs to see what the housing prices are generally like, how much they've increased year by year. Are they higher in certain areas, or are they lower in certain areas? That kind of thing. And then once I have a decent idea of what's going on, I could build a machine learning model. I could build a statistical model that predicts and forecasts the housing prices of new houses in a particular locality. And after I've done that, after I've got a reasonably working model, I can use the results in any way I want. Well, I can put them in good use. So I can use them either by myself, or I can hand it off, or I can present it to someone else who can implement those results. Great. And now we move on to the main topic of today's lecture, which is pandas. So what exactly is pandas? So pandas is a data analysis library in Python. You've already seen a library in Python that is NumPy, and pandas is quite similar to it, but it does a lot of heavy lifting when it comes to working with data. Specifically, it helps us to extract data, store it, clean it, and use it for visualizations or statistical inferences. So it does a lot of work for us. Great, so how exactly we use pandas? Import statements. So just like we imported NumPy as FP, we typically import pandas as PD in order to use it in our notebook or wherever you're using it in the program. And yeah, we need to import it if we want to use those fancy functions that pandas provides us. So if we want to do all this, we need to import pandas. And this is how we do it. So I'm going to switch over to demo. And throughout the lecture, I will be switching between slides and demos. So if you want to see that in detail, feel free to pause it and watch it again. So in the first line, I will import pandas as PD, and when it's done, I can print pandas imported. There we go. That was fairly quick. And now we can use pandas throughout the notebook. And the second reason is, why do we want to use pandas? Because we have been using quite a bit. We have been using NumPy, we've been using Python. Why do we want to use pandas? Well, I think the main reason is convenience, because when it comes to working with large data sets, NumPy and Python can get very messy very quick. So pandas is very, very useful. And the second reason is it's very easy to visualize or label the data using pandas. And the third is that pandas has a ton of built-in functions that make working with data so much easier. Switching over to the demo for a little bit. So a common task that we want to do while in a data science project, and this comes under the scrubbing phase, or like reading the data. Scrubbing phase is reading data from a CSV file. So a CSV file is essentially a common way in which we store data. So this is an example of a CSV file. Its name is data.csv, and over here you can see a list of names. So you have a bunch of column headers. So you have name, age, mystery, number of toes, and whether you like Jason Derulo or not. And over here you can see that there are a list of names, there are a list of numbers that denote ages, and so on, and they are separated by commas. So this is one of the most common ways in which we store data. We can also have things like TSV, which stands for tab separate values, in which you use tabs instead of commas to separate it. But throughout this class, we will mainly be working with CSVs. Great. So if you were to read a CSV file and use it in a program using basic Python, you can see the code. It's quite complicated. I do not expect you to understand any of this. You will definitely not be using this. So if I run it, I do get exactly what is in this file, but it doesn't look very nice. But if I use pandas, on the other hand, it's, well, first of all, just 2 lines instead of how many ever lines this is. And it's very simple. So you don't need to understand the code right now. We will get into that. Main thing is that we have a very, very nice looking table, which has the data nicely formatted, and it's much simpler. So this is the convenience part. And pandas also helps us in visualizations. So again, we don't need to worry about the code. I'll get to that later. And over here, it's essentially 2 lines. And by running it, I can get a bar graph of each person and the age and a number of toes I have. Fantastic. So that is kind of why we use pandas. And moving on, we move on to the 2 main pillars of pandas. So these are the 2 foundational elements of pandas that you're going to use all the time, which respectively are series and data frames. First one is series. So series is very analogous to a 1D array in NumPy or a Python list. And it is essentially either a row or column of elements that have particular indexes and store particular values. So over here, you can create a series explicitly by calling pd.series. And over here, you have a Python list that says pizza, soda, fries, and nuggets. If you run this command, you'll get something very similar to this. So you'll get 0 pizza, 1 soda, 2 fries, and 3 nuggets. Great. Now I'm hungry. And the second main pillar of pandas is a data frame. A data frame is analogous to a 2D array in NumPy, or a dictionary or list of lists in regular Python. And this is primarily the tool that we'll be using to work with data throughout this class. So this is very, very important. And we use it to store data represented in tables, which is the most common form in which we represent data. And we will commonly refer to data frame as df or subname underscore df, just to make sure that we know that it's a data frame. And if you look carefully at a data frame, you notice that each row and column of a data frame is a series. So if you look at this column, we'll notice that the elements, not the headed elements of pizza, soda, fries, and nuggets, are exactly the series that we use over here. And each row, so over here you have 0, pizza, and 10, that is a series as well. That is good. And now we move on to creating data frames. So for use the cool Pandas operations, we need to create data frames. And we can create data frames in a number of ways. So the most common ways are creating them from a Python dictionary, or we can create them from a NumPy array or Python list of lists, or we can read CS3 files, which is kind of what I did earlier, but we'll go a bit in depth right now. And reading CS3 files will be the primary way we'll be creating data frames, but it's good to know we can do these as well. So moving on to a demo, you can see that first of all, we can create a Pandas series from a list. So over here, we have a list of cakes. So we have chocolate, sponge, banana, and fruit. And we store this list in a variable cakes. And we call pd a series on cakes, which is similar to what we did over here. Instead of explicitly defining a list, we wrap it up in a value cakes, a variable cakes, my bad. And then we store the value in cake series, and when we print out cake series, we get something very similar to what we see over here. So you have 0 chocolate, 1 sponge, 2 banana, 3 fruit. Amazing. And now we move on to creating data frames. So for creating data frames from a Python dictionary or from NumPy array, we use a function called pd.dataframe, and we pass in relevant arguments. So moving on to the demo, you can see that over here we have a cake price dictionary. So just a reminder, a dictionary is a data structure in Python that holds a particular set of keys and respective values. So the keys are usually immutable data types. They cannot be changed. So we have cake and price, and we have a bunch of values. So the first key is cake, and the respective values is the array cakes that we defined over here. So we have chocolate, sponge, banana, and fruit bound to cake. And price has a list of prices for each cake. So this is a fairly basic Python dictionary. And when we call pd.dataframe on cake price and store the value in cake price df, and when we call cake price df, you should get a data frame which is very similar to the one we saw over here, except it's a bit smaller, and you can see that it looks very much like the one in the lecture slides. The next way that we create a data frame is from a NumPy array or list of lists. And over here, you can see that we have something that's very similar to what we defined above, apart from the fact that I'm defining it as a list of lists instead of dictionary. So I have chocolate, 10, sponge 5, banana 7, fruit 12, which are the list of cakes and the prices. And I have defined the columns explicitly. So over here, we have cake and price, which Pandas automatically bounds to the keys in the dictionary. But over here, since we don't have any keys, we need to define them explicitly. And we need to notice that Pandas lets us set a list as column names. And if you run this piece of code, you can see that it gives us the exact same thing. So this is not really the method that I had used for large data sets, because you need to define everything explicitly, and this could get really messy very quick. So you need to input a ton of values by hand, which isn't really ideal. We have better ways to do it. Better ways is namely reading CSV files. So we will primarily be working with CSV files throughout this class. And we're going to use a nice method that Pandas has called pd.readCSV. This is a quick demo. Over here, I have a CSV file called data.csv. It's saved in the same place as this notebook. And if I look at its data, it has name, age, mystery, number of toes, and lactase and ruler. So it's the same thing as before. And over here, I've defined the function pd.readCSV, and I passed in the argument as data.csv. So I pass in this file to the argument. And I need to store the value in peopledf. And now, if I run this piece of code, I can see that peopledf is exactly the data frame, which is exactly the table that's seen over here. So we have names, we have age, mystery, number of toes, and whether lactase and ruler. So this is very, very convenient because we can do it for files of any length. We don't need to define it explicitly. We just need to make sure that the file is saved in the same place. Or we can even define a path to the file. And the main syntax for using this is pd.readcsv, and we have the file name. So in an example, it was data.csv. So we put in data.csv in quotes over here. And now we move on to the anatomy of a data frame. So usually you would not have data frames that are as cute as 14 rows and 5 columns. So you may have data frames with like thousands of rows and, well, equally as many columns. So it might be a bit problematic to just go through the data frame and figure out the shape and size. So luckily we have a couple of unique operations that help us find dimensions of a data frame. The first of which is df.shape, which returns a tuple with a number of rows and columns in a data frame. So just a reminder, a tuple is a collection of numbers or objects that cannot be changed. It's very similar to write a list, but in a list, the values can be changed. In a tuple, they just cannot be changed. They are immutable. And just as a quick demo, so first of all, if I define peopledf.shape, it should return a tuple that contains 14, 5. So this particular data frame has 14 rows and 5 columns. And you can see that if I do a similar thing over here, peopledf.shape, it returns 14, 5, which is the number of rows and the number of columns. If you look at the data frame that I have over here, you can see that the indices of the rows are from 0 to 13. That means I have 14 rows. And you can see that I have 1, 2, 3, 4, 5 columns. So it seems to work, which is good. And the second way that we can find dimensions of a data frame is df.size, which returns the number of entries in the data frame. So usually this is just the number of rows in the number of columns. So over here we can see that if you have 14 rows and 5 columns, you'll have 14 to 5, which is 70 elements in the data frame. And we see that over here, if we run this piece of code, we have 70 elements. So the total number of elements over here are 70. Amazing. So now that we found the dimensions, we might actually start looking at the data in the data frame. And again, if you have a data frame with like thousands of rows and equally as many columns, you may not want to print it out because it'll be very long and very complicated. And frankly, we do not want that. So we have two very useful operations. We have df.head and df.tail, which we can use to view the first few rows or the last few rows of a data frame. So df.head returns the first 5 rows of the data frame. And we could also define df.n and pass in a parameter n for the first n rows. And over here, if I call people df.head of 3, then it prints out the first 3 rows, returns the first 3 rows rather. So if I pass an argument, pass in the argument people df.head of 3, it should return the first 3 rows. And let's say I do not pass any argument, I just open close parentheses, it will return the first 5 rows. So if we compare it to the date frame, you'll see the first 5 rows, page, release, Elton, Siddharth, Numa, are the same as over here. So it seems to work. And the second operation that we have is df.tail, which does something very similar to df.head, apart from the fact that it returns the last 5 rows or last n rows, depending on what we pass in. So people df.tail will return the last 4 rows in this case of the data frame. Just see if it works. Yeah, so if you have people df.tail, we can see that it returns the last 4 rows, which if you look over here, Addison and build twice, Addison and build twice, seems to work. So very good. And by the way, build twice is not an error. We will get back to that later. Amazing. And okay, so we also may want to know the number, what kind of columns we have, because columns are usually the kind of variables that we'll be dealing with. So it's good to know what kind of variables that we have when doing any kind of analysis. So df.columns returns all the column names in the data frame. So if I pass this, you can see that I get a list containing names, age, mystery, number of those, and like, trace, and ruler, which also is the name of the columns of the data frame. So name, age, mystery, number of those, like, trace, and ruler. I've been saying that a lot. Yeah, and the other way that we can view data is df.values, which returns all the entries in a data frame as a 2D numpy array. So just in case you want to use some numpy functions or want to convert the data frame into a numpy array, we can use peopledf.values, which returns a 2D array. So if I just show up here, there we go. So it returns a numpy array, a 2D numpy array. So it has a list of lists, and each list inside the main one has the set of elements, has each row.
Hello, everyone. My name is Elton, and I will be teaching the second part of this Pandas Part 1 lecture. You should be watching these videos after you have watched the Don's videos, or else these videos will not make any sense to you whatsoever. So to tell you a bit more about myself, I am a sophomore. My major is data science and econ, and I'm from Southern California. My fun fact is that I eat a lot of Carl's Jr. If you have any questions about this lecture or anything in general, or you just want to talk to me, my email is chanelton@berkeley.edu, and my username is eton on Discord. So this lecture will be split up into 3 different videos of 3 main preliminary things that you can do with Pandas. And I'll be switching between the presentation and the demo to show you how to use the stuff that I'm teaching you in a actual data sense. So the first thing that we will be going over is utility operations. So what are utility operations? They are programs that we run that perform very specific tasks. And these tasks are ranging from anything that allows to manipulate data and make it easier to analyze. These utility operations take in parameters that specify what conditions we want the program to run on. Most of these operations are non-mutating, and we will get into this more when I show you specific examples, but the main idea is that they do not change the original data frame in any way. They just produce a different output for data frame. These utility operations that I'm about to go over are pre-coded into the Pandas library, so once you have imported Pandas, you should be ready to go. The general format that I'm showing you here is df, where df is the name of your data frame, dot utility operation, where the utility operation is the name of the specific operation, and then any amount of parameters that you would need to specify. All right, so the main 7 operations are shown here: sort values, value counts, rename, dtypes, as type, index, and set index. All right, so I'll just give you a chance to look over those real quick before we get into the specifics. Okay, so the first one that I'll be going over is sort values. So the usage of sort values is when you want to sort the rows of the data frame for more organized and chronological data. This is especially useful when you have a lot of different data and you just want to see how one specific column plays out. The parameter is column name, which you need to include in square brackets here and in quotations. And the column name is the name of the column that you want the entire data frame to be sorted upon. So all the rows are moved according to the values of this column, not only the values of the column, but the entire row, but all the rows. The next parameter is ascending, and ascending determines whether the values are sorted from smallest to largest, so from 1 to 10, or from largest to smallest, 10 to 1. So the default value is true for this boolean, and that means that when you do not put any value for ascending, it will sort from ascending order from 1 to 10. So to get data from largest to smallest, you would set ascending equals to false, which is descending value. The inplace relates to non-mutating and it determines whether the original data frame is modified by the operation. The default value is false. All right, so let's move over to the demo and I'll show you how that happens. So first, let's import pandas as PD, which you should already know how to do, and I'll import NumPy as NP to help us a bit with our mathematical operations later on. So let's run that cell to import, and I'll import our data, and you should have already seen this data a little bit with Sadan's videos, but we're going to be diving a lot more deeper into it. So I import the data using pd.readcsv, and then the name within quotations, and then I print the data using this here. And this is when I declare that data is the name of the data frame. And we see here that our first value is name, then we have an age column, and then we have a mystery column, which I'll get into later. We have a number of toes column, and we have a like Jason Derulo column. So this is our data frame, and this is where we'll be doing our operations on. So let's say that we have all these ages, and we want to see who has the youngest age, who's the oldest age, you know, just like how the entire distribution of age plays out. So this is when we use sort value. So we have df, where df is the name of the data frame, data, dot utility operation, where it's sort underscore values, and then we have square brackets. And the square bracket is including the name of the column. So that name is age. And then we would run it to get our output. Now we see that the ages are sorted from ascending order because ascending is the default. So the smallest is me with age 2. And then we have Jason here, who is 7 years old. And everything here is sorted from ascending value. Nice. But notice how the original table doesn't change. And this is what I mean by non-mutating. So we perform our utility operation here, dot sort values, and we have this data frame. However, notice that the output of the utility operation doesn't affect the original data frame. So the data frame itself, it's still unsorted here. So now, let's say that we do want the utility operation to be mutating. So this is when we use the inplace parameter. So inplace, we would set inplace equal to true. So that means we do want it to be mutating. And then let's say just for fun, we want ascending to be equal to false. So that means that we should expect Jason earlier, who was 70 to be near the top, and me, who is 2, to be on the bottom. And we run data, we print data itself now, and we see that data itself is changed. So we see that the ascending parameter has worked. Jason is at the top, he's the oldest, and me, I'm at the bottom because I am the youngest. Okay, so on to the next utility operation, which is df.valueCounts. So what value counts returns us is a series containing counts of unique rows in the data frame. So this might not make that much sense off of the first read, but let's deconstruct it. So it returns a series, which you should know from the previous lectures. From the previous lectures, tell us that a series is a one-dimensional row, and it contains counts of unique rows in the data frame. So it'll tell us how many unique rows we have in the data frame. So this allows users to see how many unique data points appear within our data. So a very small example here is just I cut out a snippet of our data frame from the demo. And we see here we just have 5 columns. We have the name column, 5 rows, 3 columns. We have name, age, and the mystery column. So we see here that Siddhant has 17 for age and apple for the mystery value. Uma is 24, pineapple. Bill 40, apple. And notice how Bill 40, apple appears twice. So these 2 data points are exactly the same. And then our last data point is Bill 40, but one value is changed, cranberry instead of apple. So how does value counts tell us how many unique rows there are? So we go here, and this is our series. This is one-dimensional. So we see that for the data point with Bill, 40, and apple, there are 2 of them, which we can see here. And all the other ones are 1, even though Bill is exactly the same, 40 exactly the same, but cranberry is 1 off, meaning that it is its own unique data point. So let's see how this plays out in the actual demo. So let's re-import the data because we mutated it with our previous operation. So now this is our original data point, data frame again. And then let's run value counts. But before we run it, notice how value counts doesn't take in any parameters. So you would just have empty parentheses. And then notice how it's exactly the same. Bill here, these 2 are exactly the same. And there are 2 of these. And every other data point is unique. All these other data points are its own unique values. So this is very useful for large data sets where you want to see if you have any duplicates of data or any values that are just singular values on their own. Okay, the next utility operation. So the next one is rename, and this is used when you want to rename the column labels of your data frame. So the parameters that it takes in are the original name of the column that you want to change and the new name, the name that you want to replace it. This doesn't affect any of the values. It only affects the column name. The syntax here is the name of the data frame, the name of the operation, and then you must type out columns equal, and then you open up a dictionary, the original name, colon, new name, end the dictionary, and then end the parentheses. So let's go over to the demo. Let's look at our original data again. And then this time, we don't want mystery anymore. So I'm telling you now that this column stands for juice. So it's what kind of juice the person likes. So now let's make that change. And also, let's say that just for the sake of working out through our demo, we don't want this column to be named age, we want it to be named years, because that's basically the same thing. So we would have data, name of the data frame, dot rename, and then we open the parentheses with column equals, and then we open the dictionary. And then the first value, the first parameter, is the original name, which is mystery, in quotations, and then a colon, and then the name that we want to change it to, juice. And then if we want to do a second set, we would include the name of the second column that we want to change, and then what we want to change it to. And then we close it and close it. So now let's run that. And then we have here that juice has replaced mystery and years has replaced age. But again, notice how this operation is not mutating, because once we call the original data frame again, it's still mystery and still age. So now this time we want to change it. However, this operation doesn't have the inplace parameter. So we have to set it equal to itself. So the name of the original data frame, the original container, you set that equal to the data frame with the operation on it. And this time I got rid of the age and years and I just left it with mystery and juice. So I run this again, and now the data frame itself, the original data frame, now has juice instead of mystery. All right. And then now let's move on to the next operation. The next one is D types. So the usage is when we want to determine what type of variable types data frame contains. So there are a bunch of different variable types that data can take the form of, but just to review some of the basic ones, we have object, which includes strings, and you should learn what strings are from the Python bootcamp. But a quick refresher are just any letters or words that are in quotations. They could also be int 64s, which are integer values. So for example, 35, or floats, which are decimal values. So example, 35.5. And then we have bool, which stands for booleans, and those can take the form of either true or false. So now let's move on to the demo and see what kind of data types our data frame contains. So this is the original data frame once again. And then we would do data.dtypes. And notice how there isn't even parentheses for this operation, and it doesn't take in any parameters because of that. So when we run this, we get that name is an object, and object means string, and names are strings. Our age are integers. Notice how they do not have any decimal value. Juice is also an object because the juice is also a string. Number of toes is a float because they do include decimal values. Like Jason Derulo is a bool because it is a boolean. So that means it's true or false. Okay, our next operation is it touches on what D types does. So as type, you would use as type to set variable data types to see your specified data types. So this could be used when you have a column that has a data type that you don't want it to be that specific data type. So the parameters that it takes in are column names, the name of the column that you want to change the data types of, and then the new type, which I just went over, object, integer, floats, or boolean. Okay, so this is our original data frame again. And then let's say that we don't want age as integers anymore. We want it as floats because people, they could be like 16.5 if you want to include like months or some type of decimal. So I'm using the equals because there is no in place, and I actually want the original data frame to change. So that's why I use data equals and then the utility operation. So I'm opening the dictionary here, and the dictionary includes the name of the original data frame, age, and then I want the type to be float 64, which is a decimal. And I run that, and I see that now these are all decimal values. Nice. So on to our next utility operation, dataframe.index. So the usage of this is that it will just tell us the row labels of the data frame. It'll give us a range of our data frame values. And this one is pretty straightforward. We'll just run it. Notice how there are also no parentheses. So the range index, it starts at 0 and it stops at 14, a step of 1. So that means it just increments 1 at a time. From here, we see that it does start at 0, and that means that it is inclusive because it includes the 0th value. However, stop is 14, and the last value is 13. And that is because the stop value is exclusive, so it doesn't include the 14. So it goes from 0 to 13, which tells us we have 14 total values. Okay, so on to the next one, which is dataframe.setIndex. And this is used when you want to set the data frame index using an existing column. So what does this mean? It means that if we want our values within the data frame to be referenced by their specific column value, we would set that column value as the index by which we can call that row. This will make much more sense in the demo. But our parameters include the column name that you want the column name to include, that you want the operation to use as the index. And then inplace determines whether or not the operation is mutating. The default value is always false for inplace mutations. So now let's look at our original data frame again. And suppose we want the rows to be identified by their ages. So we want to be able to call, let's say, me by my age. So here, our original index is 0, 1, 2, 3, 4. So we can index by this number, right? But now we want to index by age. And we would do this by using the set index. So we come down here and we do data.setIndex and the name of the column. And I am setting this operated upon data frame into a second data frame called data2 for later use, because this will come up again in a later example. So data2 equals the original data frame and then the operation. So let's run this. And now data2 has age as the index. And all the other values are just as before, but notice how age is now used as the index.
Okay, so now we are on slicing and indexing. So what is slicing and indexing? So slicing is dividing up our data according by what we want to include. So we have complete control over the parameters by what we slice by. This is useful for isolating certain rows or columns, and it allows for cleaner and more organized data analysis. Indexing is similar to looking through library books. So think about if you're looking for a library book based on name or author or publication. This is similar to what the idea of indexing is with data frames. So each row has an index that can be called to get that row's full information. So our first method of slicing is just by using double brackets. So the usage is that it returns a data frame with only the specified columns. If you use single brackets instead of double brackets, it returns a series instead, which we already know to be one-dimensional. This allows for much more organized data analysis because we can include what columns we want and what columns we don't want. The parameters for using this method of slicing are column name, and you must use quotations because they are strings. These are names of the columns you want to include. In my example above, I show that you can use 2 different columns to get a data frame with 2 columns, and you split them by using a comma, but you could also use one column to get only 1 column wide data frame, or you can use 3, or you can use any amount of columns to get as big of a data frame as you want. So now I'll show you this in the demo. So this is our original data frame once again, the same one we've been seeing this whole time. So we have 5 different rows here, and say we only want the name and the age rows. So we would have data, the name of the data frame, double brackets, and then within the double brackets, we quote name, comma, quote age. And then when we run that, we see that it's exactly the same as this data frame. However, it's only the name and the age column. The rows, we have all the rows here. However, notice again that this does not change the original. This only produces a different output for display, but it does not do anything to the original. If we wanted to keep this sliced data frame, we would set it equal. We would store that sliced data frame in another variable. And in this case, I chose just selected. It doesn't matter what name you choose. So selected equals the sliced data frame, and then once I run this cell, it sets it equal to, and then it also prints selected. So now selected will forever be this until I set it to something else. Okay, on to the next method of slicing. So this method of slicing is lock. It's called .lock, and it essentially locates the row indexes that you put in. So the usage is that it works with row labels. And this is different from ilock, which I'll introduce to you as the next slide as the next method of slicing. But this only works with row labels. And you'll see what this means in the demo, but it returns a data frame with only the specified rows. So if you use single brackets instead of double brackets, just like the method before, it returns a series. So if you want a full data frame, make sure you use double brackets. The parameters are row index, and this is the index name of the row that you want to slice. Okay, so to the demo, this is where data 2 comes into play. And if you remember from earlier, the previous video, data 2 was when I used set index to set the index to the age column. So notice here age is the index because it's in bold and it's one step lower, and the rest are the normal columns. So say that we want to use lock to find the indexes where the index is 17 and 2. So 17 was Sedan and 2 was me. And let's just say I only want a data frame with only us two as the data points. That's when I use lock. So I use the name of the data frame, data2.lock, double brackets because I want a full data frame, and then the name of the indexes, 17.0 and 2.0. And then I get them. Notice how these are not in quotations because when I originally set index of these values, they were already set as floats. They're not strings, so you do not put them in quotations. However, if you do use set index on a column of strings, make sure that you do have them in quotations later. Okay, on to our next method. So we have lock, and then we have ilock. So ilock instead works with row integers, while earlier they worked with row labels. So row integers are different from lock. This works in essentially the same way of returning a data frame with the series, and then for single brackets and returning a full data frame with double brackets. So the row parameter, the row number parameter is the integer number of the row you want to index. So it is the order that the rows come from in the original data frame. So I will print the original data frame again. And then let's say I want the first 4. So the first 4 are labeled 0, 1, 2, 3. And these are based on the row integers, okay? So it's 0, 1, 2, 3, and then it's data.ilock, and then double brackets because we want a full data frame, and then we run that. So we see we only got the first 4. And then let's say we want to skip the 4th one and we want the 5th one. So we can just replace the 3 with the 5, and then it's 0, 1, 2, 5. Our final topic will be filtering. So what can you do with filtering in Pandas? So first we need to go over what filtering is. So filtering is essentially getting what we want according to the specifications that we set within Pandas. And it allows us to isolate values by getting rid of irrelevant data that doesn't fit our specified conditions. So the purpose of filtering is for more focused analysis because we're able to get rid of data that is irrelevant to our analysis. And it allows for easier computation too, because since data points aren't necessary, we can just get rid of them, and then the Pandas will have less runtime. So the first method of filtering is really useful because you can use it in all different types of data analysis, and it is conditional filtering. So you can see the syntax there, but I'll dive more into how the syntax works in the demo. But the usage is that you filter out values that do not pass the specified condition. And this specific syntax returns a data frame containing only the rows where the specified column values satisfy a condition. So all the values in that specified column are put under a condition, but if the value fails the condition, the entire row is removed, not only the value in the column, but the entire row. So the parameters for this filtering method is the column name. So this is the name of the column where you want the values to be set to a condition. And then the condition is a computational condition that evaluates to a boolean. And we know this to be true or false values. So an example of a numerical condition would be equals 500, which means is the value equal to 500 or not?
or it could be greater than or equal to 90. A small example here is data frame number of apples less than 300. So for every value in this column, Pandas will check if that value is less than 300. And if it is less than 300, then the Boolean value evaluates to true. But if the value is greater than 300, then the Boolean value is false. So now let's move on to the demo, and I'll show you two different examples of this. So this is the full data frame again that we've been seeing from the past two videos. So everything is still exactly the same. So let's say that we want to see, based on this data, which of these people like Jason Derulo. So this is the column of like Jason Derulo. You see there are true or false values, but you can't really like determine the entire data frame yourself. That's when conditional filtering comes into play. So this is the code, and I'll break it down more here, but this is just the entire code. So you have the name of the data frame, and then you open square brackets. And then within those square brackets, you have the name of the column. So this will get the column of like Jason Derulo as a series, and then it'll pass it into a conditional of equals equals true. So that checks whether or not the value in this series is true or not. So let's go ahead and run that. And we see that all the values here are true. So now this table only consists of rows where the column value of like Jason Derulo is true. So now let's break it down so we can really understand what's going on here. So let's take this first little snippet here where it's data of like Jason Derulo. So that isolates the series of the like Jason Derulo data frame column. So you see here that this is a series, a one-dimensional series of only this column. And it is only a series because we have only single bracket instead of double brackets. And then we check if that series equals true by having the condition now. And then we pass this Boolean series back into our original by having the name of the data frame again, and then the brackets. And then that's how we come out with this data frame. I'll show you another example. Let's look at the full data frame again and say, look at the age column. How about we only want people who are at least 23? So that means everyone who is 23 and older. So exactly the same syntax. However, this time it's a numerical operation. So we do greater than or equal to 23. And then we see here everyone with their age value. If their age is at least 23, then their row has been kept. But if it was false, then their row is removed. So let's break this down again. First, we have our series here, which isolates only the age column of the original data frame. And then once we have that series here, we run that series with the computational condition using greater than or equal to 23. So that returns a true or false value series now. So we've turned our numerical series into a Boolean series. And then by passing this Boolean series back into the original data frame with single brackets, we get the full data frame again. All right, so onto the next concept of filtering is when NaN values show up. And NaN values mean that there is no value for a single data point, and NaN actually stands for not a number. However, this cannot be confused with NaN meaning 0, because NaN is not 0. It means that there's absolutely no data for that value. And the reasons we could have NaN values is when there are errors in transcribing data or error in uploading data or any type of situation where data is left out. So there are two main ways of dealing with NaN values, but the main idea behind these methods are so that the results do not skew analysis. All right. So just to see some NaN values in our demo, I'll show you some in our data set. So suppose we only want to observe the participants' names and their number of toes. So we would have the slicing method that I showed you in a previous video using double brackets so that we get a full data frame. And we see here some people have 9 toes. Most people have 10 toes. Dixie has 11 toes. But notice here, Uma and Shannon have NaN values for their toes. So this means that they could either not have reported it, or there was an error in when the data was being reported or anything like that. But we don't have any value for their number of toes. So what can we do? So the first method is that we could just completely drop them. And the way of using .drop NA is that it drops all the rows with NaN values in the data frame. However,
So the significance of this is that you entirely remove the row that contains the NaN values. So there are just no more NaN values in your resulting data set. However, you do lose a data point. So if you were to remove a very statistically significant data point just because they had an NaN value for a completely unrelated row, that could skew your analysis. However, let's just see how we would use it for now. So I'm naming a new data frame called dropped, and it is where all the drop value, where the data frame has been dropped of all the NaN values. So then I set it equal to .drop NA, and notice how there are no parameters, it's just empty parentheses. And then once I print drop, you see that we don't have Uma anymore or Shannon, and all the number of toes have no more NaN values. However, from conditional filtering, we can see that we're checking the juice column to see if anyone likes pineapple, right? Because this series gets the juice column and then it checks if that column has a value equal to pineapple. So when we run that, we notice this is empty, and dropped is our data set, is our data frame that we just made without any NaN values. However, from the original data frame data, if we perform the same operation, we see we have Uma, and Uma actually liked juice. But because we removed her NaN value, because she didn't like toes, we removed the pineapple from the juice category. And so that's why it's a problem, because we might have just removed the only person who liked pineapple, and that could definitely skew our analysis. So instead, let's try a different method, df.fillNA, and then the parameters of value. So how this works is that all the NaN values in the data frame are replaced with a specified value. So instead of removing the NaN value, we replace all of them with a set value. And so we can put anything to value. We can use strings, we can do integers, we can do floats. And the data significance of doing this is that replacing all the missing values with the wrong value could have an effect on final analysis, because if you replace it with the wrong value that wasn't accurately reported, you could get totally incorrect results. However, this method allows you to salvage data. So in our demo case, it allows us to keep the information on Uma liking pineapples without completely removing her from the data set. All right, so instead, let's replace the NaN values with a value. So why can't we just replace it with 0? Because we cannot just randomly assume that people have 0 toes. That may be the case, but it's a very unlikely case considering everyone else has, 10 toes or 9 toes or 11 toes. So the safe bet is to use the mean of all the previously given values to us. So how can we calculate this? We can calculate it with np.mean. And then mean will take in a series here. And this series is the column from data of number of toes. So it'll take in all the number of toes, and then it'll give you a mean value. And that mean is 10. Because if we come back here and we look from all the non-NaN values, this is from our drop table, we can see that, there's a 9 and there's an 11, but everything else is 10, and that averages out to 10 toes. So if I do data.fillNA, our operation, and then the mean value that I stored over here. So now we have Uma again. And notice how this time she has 10 toes instead of an NaN value, and she's kept in our data set with an actual value for number of toes. So this allows us to keep the pineapple within the juice category, but it also allows us to deal with the NaN values. However, a potential statistical problem could be that, Uma could have 15 toes, but we would never know. But our statistical safe bet is to use the mean. So just know that from case to case and from data analysis to data analysis, use discretion and use the correct method of dealing with NaN values. Okay, so that concludes the video. If you have any questions, do not hesitate to email or Discord PM Sidon and me. We'll be ready to answer any questions you have. Thank you.